Here we are. This is our last section of notes before we're finished with calculus for the year. So before we get into what's called the L'Hopital's rule, take a minute and remember what you remember about evaluating limits back from chapter 2. You're going to evaluate these 3 limits. So stop the video and try these 3 problems. So hopefully you didn't have too much trouble here. The first one you can evaluate with a substitution. There's no problem once you substitute in, no 0 over 0 or infinity problem. Second one you probably evaluated by factoring and canceling. And the third one you probably evaluated by thinking about which term dominates in the numerator and the denominator. So when we have complicated limits problems, and some problems that are even more complicated than these, like a lot more complicated than these, we can use what's called L'Hopital's rule to simplify them. And L'Hopital's rule is going to apply, or we might find that it applies, whenever using substitution leads to a 0 over 0 or infinity over infinity. Each of those is called an indeterminate form. And notice that they imply that L'Hopital's rule is really going to only possibly apply in a place where we're trying to find the limit of a ratio. So the limit of something that looks like a fraction. And here's how L'Hopital's rule goes. Where am I? If you have some ratio of 2 functions, so let's imagine you have f over g, and you want to find the limit as x approaches a of f of x over g of x, you can, if that would give you 0 over 0, if substitution in would give you 0 over 0, then you can evaluate f prime of a divided by g prime of a, and that will be exactly equal to the limit. So we're going to try that from the first example. When we tried substituting in -2, get the whiteboard up. So this is just us checking. If I replace x with -2, I'm going to get -2 squared minus 4 over -2 plus 2. And that does in fact make 0 over 0. So notice that we can only try this if plugging in gives us 0 divided by 0. Since that worked, and I can look at both of those numerator and denominator functions and tell that their derivatives would exist, I'm going to evaluate a new problem. I'm going to find g prime, which is going to be, f prime, which is going to be 2x. This limit is going to equal 2x over, well, the derivative there is 1. So this is going to be the same as finding 2x over 1 when x equals -2. So that's going to be 2 times -2 over 1, which is -4, which should be the exact same answer you got when you solved this problem at the beginning of the video, I expect, by using factoring and canceling. So notice, for some cases, you might find that L'Hopital's rule goes even faster. You just have to make sure that you check that those, we call them the hypotheses, the suppose that parts have to work. So if substituting in gave you 0 over 0, and the derivative of the top and the derivative of the bottom both exist, then you can find the derivative of the top with a plugged in divided by derivative of the bottom with a plugged in. And that will give you the same result, the limit. So it turns out L'Hopital's rule is even more powerful than that example that we just tried. You can use L'Hopital's rule even if, when you find that derivative over the derivative, if that gives you another indeterminate form, you can do it again by finding the second derivative, by finding the third derivative. You can chain together as many of these as you need to, as long as you check that every time you try it, substitution would give you 0 over 0. So I want to emphasize early on, I want you to build this habit. If you want to try to use L'Hopital's rule, and you will definitely have to use it on the AP test, I absolutely want you to make sure that you checked substitution first. So I'm going to take this problem. I'm going to just draw this big arrow over here because I don't want to mess up the place I'm going to use later to use L'Hopital's rule. But I'm going to double check that I'm going to plug in 0. It's going to be 1 minus cosine of 0 over 0 squared. And that makes 1 minus cosine 0 is 1 minus 1 over 0, which does in fact make 0 over 0. Okay, so I'm going to try L'Hopital's rule. Here's what I do. This is the same as the limit as x goes to 0 of, I'm going to take the derivative of the numerator and the derivative of the denominator. The derivative of 1 is 0. The derivative of negative cosine of x is the opposite of sine of x over 2x. And I can try again. That's going to be, what do I want to do? I'm going to double check. If I replace x with 0, I'm going to have negative. The sine of 0 is 0. And 2 times 0 is 0. So I used L'Hopital's rule, but I got 0 over 0 again. So I'm going to keep the chain going. I'm going to take the limit as x goes to 0 of, I'm going to find the derivative of the numerator and the derivative of the denominator. Well, negative sine of x is really positive sine of x. The derivative of sine of x is cosine of x. And the derivative of 2x is 2. Now I'm going to evaluate again. If I replace x with 0, I'm going to get cosine of 0, which is 1. And that denominator is 2. There's no place to substitute the x. Here's your final answer. So notice I got to use L'Hopital's rule twice in a row to find my answer. So that's what we call the stronger form of L'Hopital's rule. And here's the stronger version. That 0 over 0, it might not be 0 over 0. You might have an infinity over infinity. Or your that x value that you're interested in approaching might be infinity. L'Hopital's rule is still going to work. So that third example from the top of the page, watch this. So imagine plugging in infinity. I'll do that over here. That's going to be sort of like infinity squared minus 4 over 3 times infinity squared plus 2, which gives us essentially infinity over infinity, which is what we call an indeterminate form. So I'm going to try L'Hopital's rule. It's going to be the same as the limit as x approaches infinity of derivative of the top over derivative of the bottom. This is going to be 2x over 6x. Now at this point, you could notice that 2x over 6x simplifies to give 1 over 3. Or you might also decide that you got excited and you want to use L'Hopital's rule again, because you could imagine replacing x with infinity. You'd have infinity over infinity. So we'll try L'Hopital's rule again. This is going to be the limit as x approaches infinity of derivative of 2x is 2. The derivative of 6x is 6, which is equal to 1/3 no matter what x is. Final answer. Okay, at this point, lots of students say, hey, L'Hopital's rule is pretty fast and pretty cool. It makes finding the limits of at least functions that look like quotients makes it a lot easier than all that stuff we did back in chapter 2. So I just want you to take a minute. I didn't do it in chapter 2 to torture you. I want you to stop and write yourself an answer. Why did we not learn L'Hopital's rule back in chapter 2, back when we were first evaluating limits? So you're going to write your best answer there. And then there are these multiple choice practice questions for you to do. You might like to stop the video and do them now, or you can do them at the end of the video. I'm happy either way. And then I want to talk about L'Hopital's trap. You have this powerful new tool, L'Hopital's rule, for finding limits, especially limits of functions that look like fractions, that look like ratios. So here is a picture of chapter 8. This is page 451, number 60. My request to you is you give me your best answer for letter B. I provided this picture here so that you don't have to actually go dig out your textbook. And you can see this is the teacher's edition. You can tell right away the answer to question A is 0. think you could probably figure that out by using, that's not the picture that goes with it. But you could use whatever you want to use. You could use L'Hopital's rule, you could use a table, you could use your calculator. You'll find that the limit is 0. So, if we know that the limit is 0, would you please examine the work that's presented as part B and find out how did somebody get the answer 1/2? Because 1/2 is not correct. There's a very common error that's been made, and I want you to read what I wrote on your notes paper, see if you can find that common error. And then a couple problems from your textbook. That's it for notes this year. Congratulations, guys. You made it to the end.